There are shipwrecks resting on the ocean floor that no human being will likely ever see with their own eyes. Not because the technology doesn't exist, not because courage is in short supply, but because at certain depths, the ocean ceases to be an environment and becomes something closer to a verdict. A permanent, geological verdict delivered in darkness, cold, and pressure that no engineering triumph has yet fully overturned. Some of these vessels lie deeper than Mount Everest is tall. Others rest in trenches so geographically remote that reaching them demands longer journeys than certain orbital space missions. Thousands more may exist in regions of the seafloor that human eyes have never directly observed, not estimated, not approximated, but genuinely never seen. We know more about the surface of Mars than we do about the deepest floors of our own ocean. That is not a metaphor. It is a measurement. And yet the strangest part of all of this is not the depth. The greatest barrier is not darkness. It is not cold. It is not even pressure. The real obstacle is what happens when every one of those forces operates simultaneously, without interruption, without mercy, and without any of the gradual warnings that most extreme environments provide before they become fatal. The deep ocean does not threaten. It simply ends things. Most people understand pressure in the abstract. Few appreciate what it means in physical, structural, and biological terms at extreme depth. Water does not simply rest above you. It accumulates. It stacks in layers. Every 10 meters of descent adds another atmosphere of force pressing from every direction at once, not just from above, but laterally, from below, from angles that human intuition never naturally accounts for. There is no direction that offers relief. At 1,000 meters, ambient pressure reaches approximately 100 times the atmospheric pressure experienced at sea level. At the depth where Titanic rests, around 3,800 meters, the pressure climbs to roughly 380 atmospheres. At the deepest points of the ocean, the Challenger Deep in the Mariana Trench, pressure surpasses 1,100 atmospheres. At those figures, steel deforms, plastics behave like viscous fluids, airspaces collapse completely. A human body suddenly exposed at such depth would not drown. The lungs would compress before water could enter. Death would not arrive in minutes. It would arrive in fractions of a second. And yet, and this is what makes the deep ocean so intellectually strange, pressure alone is not what stops exploration. Because pressure is a problem engineers have learned, at great cost and ingenuity, to solve. The real problem begins after pressure is addressed, because solving one barrier always reveals the next. Humans have already proven, definitively, that the deepest ocean is reachable. The bathyscaphe Trieste descended to Challenger Deep in 1960. James Cameron made the same journey alone in 2012 aboard the Deep-Sea Challenger. Modern, remotely operated vehicles and crewed submersibles have followed. But what those missions demonstrated was not that deep ocean exploration is routine. They demonstrated that it is closer in engineering philosophy to spacecraft construction than to conventional submarine travel. Crew compartments in deep submersibles are typically titanium spheres, barely 1.5 meters in diameter. The walls may be thicker than a human forearm. Every weld, every bolt, every viewport is calculated and recalculated against a single catastrophic failure mode: implosion. Unlike the vacuum of space where pressure differential pulls outward and failure tends to be gradual and sometimes survivable, the deep ocean pushes inward from every surface simultaneously. There is no partial failure. There is structural integrity, and then there is instantaneous, total collapse. The transition between those two states takes less time than human perception can register. This asymmetry, the fact that the margin between survival and obliteration is measured not in degrees, but in a single threshold, defines every calculation deep ocean engineers must make. Not how deep the vehicle can theoretically go, but how much confidence the mathematics actually justifies. Even if pressure is solved, a second problem emerges that is harder to engineer around: finding the wreck at all. The deep ocean is not simply deep. It is vast on a scale that resists human intuition. The abyssal plains, the flat, cold, nearly featureless expanses covering much of the deep seafloor, span an area larger than all the continents of Earth combined. Current estimates suggest that roughly 3/4 of the seafloor still lacks high-resolution sonar mapping. We have better charts of the lunar surface than of our own ocean bottom. That means a significant number of deep shipwrecks may not merely be difficult to visit. They may be effectively lost. Known to have sunk in a general region but absent from any chart, any coordinate, any confirmed discovery. Even when coordinates exist, reaching a wreck site can resemble searching for a single structure buried somewhere in a lightless desert spanning thousands of kilometers. Visibility without artificial illumination is absolute zero. Sediment settles slowly but continuously, shrouding hulls and burying debris. Deep currents distribute wreckage across distances that can exceed several kilometers from the point of sinking. Sometimes research expeditions arrive at verified coordinates and still fail to locate the vessel. Depth does not merely hide shipwrecks. At sufficient scale, it erases them from practical geography entirely. Below approximately 1,000 meters, the ocean enters a regime of permanent cold. Temperatures hover just above freezing throughout the year, unaffected by seasons, unaffected by anything occurring at the surface. This cold is not dramatic. It is simply constant, and that constancy changes everything. Electronics designed for temperate environments fail unpredictably. Lubricants thicken beyond operational tolerances. Materials that perform reliably under laboratory conditions develop brittleness under sustained cold. Battery chemistry slows. Seals that held perfectly during testing begin to behave differently after hours at depth. And because no repair is possible during a dive, every small failure cascades in an environment that offers no second chances. Yet the same cold produces a remarkable paradox. It preserves. Microbial activity is suppressed at low temperatures. Oxygen at depth is limited, which slows oxidative corrosion. Some deep wrecks, as a result, show deterioration rates significantly slower than shallow water equivalents exposed to warmer, more oxygenated water. Certain vessels discovered at depth appear almost suspended, structural members intact, objects in place, the geometry of catastrophe still legible in iron and steel. This raises an obvious question. If these wrecks are preserved, why not bring them up? Because lifting from extreme depth may be harder than reaching it. A cable long enough to span 6,000 meters becomes catastrophically heavy under its own weight before it can lift anything else. Surface waves, even moderate ones, translate into whipping forces along a cable that become amplified and destructive at depth. Engineering a lift system capable of handling that dynamic tension over distances that eliminate direct observation while maintaining precise positioning above a moving ocean remains beyond practical economics for any but the smallest artifacts. Most deep wrecks will stay where they are, not by choice, by physics. There is a barrier beyond engineering that receives less attention: what the experience actually does to human psychology. Deep submersible pilots operate inside titanium spheres where standing is impossible and moving freely is not an option. Descent takes hours. The surface becomes unreachable during that time, not difficult to reach, but physically, literally unreachable within any rescue window. Communication involves transmission delays. Ambient sounds, hull contractions from thermal stress, structural settling are indistinguishable at first from sounds that would precede catastrophic failure. Pilots must learn to remain calm in the presence of noises they cannot immediately identify, in an environment where their nervous systems are correctly detecting that something is wrong simply by the fact of being there. Some who have made these journeys describe the psychological profile as closer to spaceflight than diving. Total dependency on engineered systems. No external reference points, no rescue. The knowledge that the margin between survival and death is a single bolt, a single seal, a single overlooked calculation. Technology may make these depths reachable, But nothing in human evolutionary history prepared the nervous system for the particular silence of 4,000 meters below the surface. There is a final barrier that is almost never discussed in accounts of deep ocean exploration, perhaps because it is prosaic, and this subject deserves more poetic treatment, but it is in many ways the most decisive. Operating a surface research vessel costs tens of thousands of dollars per day. A single deep submergence vehicle may represent years of engineering development and continuous, expensive maintenance. A descent to 4,000 meters requires hours going down and hours returning, consuming an entire operational day to produce perhaps 2 to 4 hours of bottom time. Weather can cancel missions without warning. Equipment failure can terminate expeditions at any point. Many deep wrecks are not unexplored because they are unreachable. They are unexplored because the cost of reaching them cannot be justified by the information that would be recovered. This is a brutal and clarifying truth. Exploration is not simply a matter of capability. It is always also a matter of what the knowledge is worth against what it costs to obtain. And sometimes the answer, examined honestly, is that the wreck teaches more by remaining undisturbed. Steel becomes substrate for deep water organisms. Hull structures provide rare hard surfaces in a benthic environment dominated by soft sediment. Microbial colonies transform iron into architecture. Over decades and centuries, a ship stops being a machine and begins being an ecosystem. Human engineering becomes biological infrastructure. The deepest wrecks are not simply resting. They are being metabolized by a world that was here long before they arrived and will continue long after their last recognizable structure dissolves into the sediment. So why can humans not reach the deepest shipwrecks? Because depth is only the entry point of the question. Pressure resists the body, cold slows and destabilizes machinery, darkness erases geography, distance isolates every mission from any possibility of rescue. Cost constrains ambition, scale overwhelms even well-funded expeditions, and risk inhabits every descent in a way that no engineering document can fully quantify. But perhaps the most honest answer is this: the deepest shipwrecks may not be unreachable. They may simply exist beyond the boundary where visiting them produces value commensurate with what reaching them demands. And that realization may say more about our planet than it does about our limitations. Because even now, in an era of satellite imaging and autonomous robotics and materials that were science fiction a generation ago, vast regions of Earth remain places where nature still sets the terms, places where human history sinks quietly into geology, where machines become habitats, where time continues its work long after human stories have concluded. Some frontiers exist not to be conquered, but to be understood as frontiers. At Sunken Realms Deep, we explore the places where human history meets Earth's most extreme environments, where pressure, darkness, and deep time continue shaping stories that most people will never witness directly. Because sometimes the greatest discoveries are not about how far we can go. They are about understanding, with precision and humility, why some places remain permanently beyond us.